In this lecture, I will share how to derive an expression for electric field due to a plane charged sheet by using Gauss law of electrostatics. For this purpose, let me consider a sheet of any size which is plane. Suppose this sheet is positively charged. When the sheet is positively charged, then electric lines of force will come out of it in both the direction, upward as well as in downward direction. So these arrows represents electric field due to this charged sheet. Our question is, what will be intensity of electric field at any point? Let me suppose the point is P, and this point P is at some distance. Let me suppose the distance is from the sheet. Suppose the distance is R. Question is, what is the magnitude of electric field at this point of observation P? This electric field can be found by using Gauss law. For applying Gauss law, we shall imagine a cylindrical shaped Gaussian surface passing through this point of observation and symmetrical about this sheet of charge. Means half of the cylinder will be taken above the sheet and rest half will be taken below the sheet. So the cylinder is supposed to be bisected at the position of sheet. So this distance and this distance both will be equal. Let me suppose both the distances are equal to r. Let me remove this. This is point of observation P. Gauss law says total flux linked with this closed cylindrical surface is equal to 1 over epsilon naught times the total charge enclosed in the surface. Means charge supplied by only this portion of sheet will be counted. Let us suppose all these three areas, this one, this area at the top of cylinder, area at the bottom of cylinder, suppose all these areas are equal to A. Magnitude of area is A. Now according to definition of flux, I can write closed integral E vector dot ds vector total flux equal to 1 upon epsilon naught multiplied with charge q. Suppose q is the charge due to this circular portion of the surface of sheet. In order to find q, let me suppose sigma as surface charge density of the sheet. Means charge per unit area is sigma, then charge enclosed in this circular portion of area A, as I have supposed earlier, it will be q is equal to sigma multiplied with A. So we have found the value of q to be put in this equation. In order to solve this left hand side of Gauss law, let me call this as equation number 1 and this as equation number 2. In order to solve left hand side, I will split this closed integral into three open integrals. So we can write E vector dot ds vector over surface S1 plus E vector dot ds vector over surface S2 plus E vector dot ds vector over surface S3 is equal to 1 upon epsilon naught multiplied with sigma into A. Using this equation number 1, I have written this. Now what is the meaning of S1, S2 and S3? S1 is this total circular area at the top of cylinder. S2 I have supposed circular area at the bottom of cylinder, and S3 I have supposed the curved surface area of the cylinder. That is how I have separated closed integral into three open integrals. In order to solve various integrals on left hand side of previous equation, let me consider elementary area on each of the three portions. ds vector, small area vector is always having direction perpendicular to its plane. Similarly, an elementary area ds vector on this curved surface will be in this direction, and elementary area on this bottom of cylinder will be in this direction. This is ds vector. So using these we can derive expressions for various integrals. In case of S1 surface, electric field and this area vector elementary ds vector are parallel to each other. So their dot product, that we call it S1, can be written as E ds cos 0, because angle between electric field and ds is 0. Similarly, in case of second surface area S2, this bottom area, ds vector and electric field are again parallel to each other. So we can write E ds cos 0. Now let us come to third curved surface area S3. In this case, so elementary area ds vector and electric field are perpendicular to each other. So we shall write E ds cos 90 degree, because a vector dot b vector is equal to ab cos theta, and on right hand side I have already written equal to sigma a divided by epsilon naught. Now cos 0 is 1, this is cos 0, and cos 90 is 0, this integral will become 0. So we are left with E ds over S1 plus E ds over S2 plus 0 is equal to sigma A divided by epsilon naught. Now electric field can be taken out of integral being constant. We are left with ds over S1 plus E integral over S2 equal to sigma A upon epsilon naught. This will give us answer for the integral ds over S1 will be S1 plus this area will be S2, and right hand side is same, sigma A upon epsilon naught. Now we have already supposed that all these areas are equal. This is area A, this will also be A, this will also be E. So we can write E into A plus E into A is equal to sigma A divided by epsilon naught. By solving this equation, we can prove that electric field is equal to sigma upon 2 epsilon naught. This is the final expression for electric field at point of observation P, due to this sheet of charge having surface charge density as sigma. That's all.